This is Algebra 2 with Trig. We're working on 2b.2b. We're doing the binomial theorem today. Binomial theorem starts with Pascal's triangle. We need to know Pascal's triangle. So all these numbers and infinitely number of more rows create Pascal's triangle. There's a lot of patterns that go on with Pascal's triangle. But what we want to recognize is that if you add the two numbers above it and end with ones, you can create what the next row is going to be. So if we add the two numbers together that are right above it and throw ones on the end, you'll see what the next row is in Pascal's triangle. So everyone is able to create the Pascal's triangle. It's not a matter of memorizing it. But you can create it. So you have 5, you have 10, 10, 5, 1. So your sixth row is going to be 6, 15, 20, 15, 6, and 1. And you can continue on. It's infinite. There's a lot of patterns that go on with Pascal's triangle. But for what we're doing today, we only need to know what are the rows. Notice that the top row is called the 0 row. Then we call this our first row. Then the row with the 2 in it we call our second row. The row with the 3 in it we call our third row, our fourth row, our fifth row. So we're going to choose the row we need based off of our second number that's in it. Call that the 0, the first, second, third, fourth, and fifth row, and so forth. So when we do the binomial theorem, what we're doing is taking a binomial and we're raising it to a power. We have a very complicated looking general formula that relates to these combinations that are parts of these values. That's a whole nother lesson. But if you know where these numbers came from compared to the numbers above them, we'll just keep moving forward. Write the coefficients of each term using the nth row of Pascal's triangle. So if our exponent is n, we would use the nth row. If our exponent is 5, we would use the fifth row. Remember that the top row is called 0. And then we start to count 1, 2, 3, 4, and 5. Then we're going to take our first term, working left to right, and we're going to expand the exponents in increasing order. And we're going to increase, I'm sorry, no we're not. No we're not. We're going to decrease them. Apologize. Decreasing order, starting with our nth value, whatever we're going to start with. Whatever our exponent is, we would count down from there. And then working left to right, we'll take our second term, which would in this case be the b of the binomial. In each expansion, when you're calculating it out, using exponents in increasing, there's my increasing word, from starting with 0, 1, 2, 3, 4, 5, and all the way up to whatever your n value is. and then we simplify. So let's get in here. No better way than to practice it. So you first come up with the first 6 rows of Pascal's triangle. Keep your eyes away from the answer key up here. Can you create it without looking at the triangle above? You can pause the video, give that a try. I apparently went up through 7, but that's all I could fit. Just showing you that it continues. There's no end to the Pascal's triangle. So if we're going to use Pascal's triangle with the binomial theorem, take a look at our binomial that we're working with. X plus 4 to the 5th power. This is the power. Power of 5. So we're going to use the 5th row of Pascal's triangle. The 5th row of Pascal's triangle is 1, 5, 10, 10, 5, and 1. That's the 5th row of Pascal's triangle. When we do our calculation, we're going to need to use those numbers, but we're going to spread them out with big gaps in between. So because this is a 5, we're going to the 5th row. We're going to the row that has a 5 in it. 5th row. So we write down the number 1. Leave yourself a good gap. 5, 10, 10, 5, and 1. From left to right, include the first term. X is going to be our first term. The x value is the first term, so we're going to put an x next to every one of these numbers. That's easy enough. And using exponents in decreasing order, starting with the n value. The n value was the power that we have. The n value is going to be the 5. So we start out with x to the 5th power, x to the 4th power, 3rd, 2nd, 1st, and 0. It will always count down to 0. Then we're going to take our second term, which is the 4. Four is our second term. No need to say positive 4 or plus 4. We just call it 4. We need to use parentheses in here to show that we're multiplying. We're not adding it to the x. We're multiplying it to the x. And we use our exponents in increasing order, starting with 0. 0, 1, 2, 3, 4, and 5. We're going to place a plus in between, or right in front of every term of our Pascal's triangle. Don't put an x in between the x and the 4. Don't put a plus in between the x and the 4. Put your plus before each term of your Pascal's triangle. Now we just simplify. Well, we have 1, 4 to the 0 power is also 1. So this is x to the 5th power times 1 times 1. That's just x to the 5th power. This here would be 5x to the 4th power. 1 to the 1st power, of course, or 4 to the 1st power is still just 4. You can calculate that out right now if you want. Plus 10x cubed, 4 squared is 16. So I'm not trying to do too much in my head at a time. I'm just simplifying what 4 squared is. I'm going to simplify what 4 cubed is. Plus 10x squared, 4 cubed is 64. 5x to the 1st power, well, we don't need to put a 1 on it. 4 to the 4th power is 256. And 1, x to the 0 power is also 1, so 1 times 1 times 4 to the 5th, which is 1024. And we finish up. X to the 5th. 5 times 4 is 20. X to the 4th. 10 times 16 is 160. X cubed. What are we going to write in the next term? Whenever you multiply by 10, you're just putting a 0 after your multiple. So 64 times 10 is 640, x squared. This one's a little bit more complicated. 5 times, this is going to be 1280, and then 1024. There, we multiplied it out. So this is in replace of writing our parentheses out 5 different times and keep double distributing all the way through. You can argue if it's easier or more difficult. It definitely has less rows that you have to work with, less terms that you have to collect. All right, on our flip side, write out your Pascal's triangle until you run out of room. How many rows can you write until you run out of room? Pause the video, give that a try. One, 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 1, 2, 1, 3, 3, 1. 2 numbers above, 2 numbers above, 5, 10, 10, 5, and 1, 1, 6, 15, 20, 15, 6, and 1. Here's somewhat of a complicated one. This is to the 4th power, so that makes it really nice. So the 4th degree. So we're going to look at the 4th row of Pascal's triangle. 1, 4, 6, 4, and 1. Those are the values we're going to be working with. So we spread those out with plenty of room in between each one. You might even turn your paper sideways and write it out the long way. So you have more room. Either way you like to do it. So now we're going to take our first term, which is 2m, and write those in there. We write them in decreasing order, starting with the power that we're working with. So 4, 3, 2, 1, and 0. Then we take our second term. That's negative n. So negative n, you need to use parentheses here. Now some people might teach it as using the negatives in a special pattern that's going to be the final result. You could do that, but I like to show that the negatives fall into place just the way that they're supposed to using algebra. So I would use that as my second term. 0, 1, 2, 3, and 4. Notice that the exponents add to be 4. 3 and 1 adds to be 4. 2 and 2, 1 and 3, 0 and 4 add to be the fourth power. We're putting our pluses in front of each Pascal's triangle number. Now we simplify this. Don't get intimidated by the simplifying, just do one step at a time. The 1 and any value to the 0 power is 1. So we have 2 to the 4th, m to the 4th. We have 2 to the 3rd power, m to the 3rd power. We still have negative n, and we don't need to write the first power, because that means you just have it once. Plus 6, 2 squared, m squared. Now what happens when you square a negative? It becomes a positive, so you're actually going to have just n squared. You don't have the negative there anymore. A negative times a negative is a positive. Plus 4, 2m, and negative n cubed. When you cube a negative, you still have a negative, and n is being cubed. And this last one is going to be 1 times 1 times n to the 4th power. Again, it's an even degree, so the negative becomes a positive. Then we finish this up. Actually, I'm going to write 2 more rows. This is 16. Now, careful with your negative. You can use it right now if you want. Negative times your positive makes a negative. 4 times 8m cubed times n. 2 to the 3rd power is 8. Still using my m to the 3rd, still n to the 1st power. I just use my negative out in front. No negative here. So this is 6 times 4m squared, n squared. Whoops. This has your negative. Negative and a positive makes it a minus. 4 times 2m n cubed. If you want to multiply those out right away, you can. So our final answer is 4 times 8, which is 32. 4 times 6 is 24. Negative 4 times 2 is negative 8. And we multiplied it out. There's the binomial theorem. One pattern I didn't point out is when this is a negative, I place the negative inside the parentheses. I made the comment that some teachers, some tutors might say, don't put your negative there, just place it at the very end. Notice the pattern that's going to happen. Positive, negative, positive, negative, positive. That's going to happen every time you have a negative in your binomial. When you're raising your negative to the 0 power, you'll always get a value of 1, so this will always be positive. When you raise it to the first power, you'll have that negative no matter what the other numbers are. When you square a negative, you'll always get a positive. When you cube a negative, you always get a negative. And you raise it to an even power, you always get a positive. So some people just treat it with pluses all the way through, and on your last step, say plus, minus, plus, minus, plus. Your choice. I suggest using the negatives and then calculating it through.